The suspension system underneath a 2026 Rolls-Royce is built on the same mechanical principle as a Victorian horse carriage. Not similar. Identical. A steel spring, a tube of oil, 140 years, zero fundamental change. Mercedes called it evolution. Porsche called it perfection. The engineering world called it an unsolvable trade-off. A battery company from Shenzhen called it an opportunity. In 5 years, BYD didn't improve the suspension. They made it obsolete. Pick up any luxury car brochure from 2026. Open it to the chassis section. You'll find language engineered to sound like science fiction: magic body control, active ride dynamics, adaptive chassis intelligence. The copywriting is sophisticated. The implication is unmistakable. You are buying cutting-edge technology. Now strip all of that away. Ignore the leather. Ignore the noise insulation and the 64-color ambient lighting. Cut straight through to the physical architecture that actually connects your body to the road. What you find is this: a coiled steel spring and a metal tube filled with hydraulic oil. That's it. That is the fundamental suspension system of virtually every road vehicle ever produced, from a horse-drawn carriage in Victorian England to a $250,000 Rolls-Royce Ghost rolling off the production line in Goodwood today. The spring carries the weight of the car. The oil-filled tube, called a damper, slows down the spring's compression and rebounds so the car doesn't bounce continuously after hitting a bump together. These two components form the mechanical DNA of modern ground transportation. A trained engineer from 1885 would look under a modern Porsche Panamera and recognize every single principle at work. This isn't engineering evolution, it's fossilization wearing an expensive suit. But the deeper problem isn't the age of the system. The deeper problem is its fundamental behavior. A traditional suspension system is, by definition, reactive. It waits. The wheel encounters a pothole, gets driven violently upward, and only then does the damper begin its response, forcing hydraulic fluid through narrow internal valves to convert kinetic energy into heat. That sequence has a name in the engineering world: hysteresis. The lag between road impact and suspension response. And here is what makes that lag so significant. It is not a software problem. It cannot be fixed with a faster microprocessor or a more powerful onboard computer. It is a physical limitation imposed by the behavior of fluids. Oil has viscosity. It resists flow. It takes measurable time to pressurize and move through valve orifices. No matter how sophisticated the electronic controls of a modern adaptive damper become, the hydraulic fluid underneath is still obeying the same physics it obeyed in 1960. For a century, the automotive industry presented this constraint as an immutable law of nature, an unavoidable trade-off between ride comfort and handling precision that engineers could only manage, never eliminate. That was not a fact. That was a convenient story built on a foundation that was never truly challenged until now. To fully grasp the scale of what has changed, you need to understand two specific moments in automotive history, 2 points at which the industry encountered the solution, recognized it, and deliberately chose to walk away from it. The first is 1992, the Williams FW14B Formula One car. Williams Engineering had developed a fully active hydraulic suspension system capable of reading road conditions in real time, calculating the precise force required at each corner of the car, and adjusting ride height proactively rather than reactively. The effect on performance was so overwhelming that competing teams had no meaningful response. The car was aerodynamically stable in conditions that would have unsettled any conventionally suspended machine. The FIA banned it, not on safety grounds, but because it was rendering the competition structurally irrelevant. The unspoken acknowledgement embedded in that ban was decisive. Active suspension works. Then the sport buried the technology and moved on. The second moment is quieter, but ultimately more consequential. Dr. Amar Bose, the founder of the Bose Corporation, and one of the most accomplished acoustical engineers of the 20th century, spent 30 years and hundreds of millions of dollars of his own capital pursuing a single radical idea: eliminate hydraulic fluid entirely, and replace it with electromagnetic linear motors. Use direct electrical force instead of fluid pressure. Remove the lag at its source. His prototypes were extraordinary. Test vehicles demonstrated ride quality, so complete that passengers described feeling nothing across surfaces that would ordinarily be punishing. Body roll in corners was effectively eliminated. One prototype in footage that remains stunning to watch could jump over physical obstacles placed in its path during controlled testing. The automotive industry looked at all of this and declined. The official objections were weight, complexity, and energy consumption. The actual obstacle was simpler and more fundamental. The Bose system demanded enormous quantities of electrical power, and the standard 12-volt architecture of internal combustion vehicles simply could not supply that power without weight and cost penalties that made the entire proposition commercially unviable. The physics was solved. The power source wasn't ready. What those engineers failed to anticipate was the electric vehicle revolution, and specifically, the emergence of 800-volt battery architectures. Because the moment a vehicle carries an 800-volt high-capacity battery pack, the power equation that killed the Bose project reverses completely. Suddenly, the energy requirements that made electromagnetic suspension impractical become not just manageable, they become almost trivial relative to the total system capacity available. That is the window BYD walked through. BYD began as a manufacturer of rechargeable batteries for consumer electronics in Shenzhen in the 1990s. Today it has achieved something that the combined chassis engineering legacy of Mercedes, Benz, BMW and Porsche has not. It has mass-produced and commercially deployed a linear motor suspension system in vehicles that ordinary buyers can purchase. The system is called DiSUS, and it is worth being extremely precise about what this technology actually is, because most mainstream automotive coverage has either oversimplified it or compared it to systems it has nothing in common with. This is not air suspension. Air suspension replaces a steel coil spring with a rubber air bladder, softer, more adjustable, genuinely more comfortable than conventional springs. But it remains fundamentally reactive. Compressed gas still takes time to expand and contract. The underlying hysteresis problem is only modestly reduced. Air suspension is a refinement of the Victorian architecture. DiSUS is a replacement of it. The DiSUS system contains no hydraulic fluid and no compressed gas. It is entirely electromagnetic. At each corner of the vehicle, a three-phase linear motor, a compact electromagnetic actuator, is integrated into the suspension assembly within the wheel arch. When electrical current is applied to these motors, the response is not the slow pressurization of fluid through valves. It is the direct generation of mechanical force through electromagnetic induction. Linear, immediate, precisely calibrated. The system's response time is 10 milliseconds, from sensor input to physical mechanical output. To contextualize that number, the human brain requires between 200 and 250 milliseconds to consciously register a visual threat. A single blink of the eye takes roughly 100 milliseconds. The DiSUS system reads the road surface through a combination of LiDAR scanning and accelerometer data, computes the force vector needed at each individual wheel, and physically repositions the suspension 20 times faster than you can perceive that a road irregularity exists. This enables what engineers have theorized about for decades without being able to practically build true skyhook suspension behavior. The conceptual model is simple. Imagine the car's body is not connected to its wheels from below, but suspended from an imaginary fixed point in the sky above it. The wheels articulate dynamically beneath the chassis, in response to the road surface. The body itself remains level relative to the horizon, as if floating. The DiSUS motor can extend a wheel downward into a depression and retract it again before the vertical energy pulse has time to travel through the chassis into the cabin. The road disturbance is intercepted and neutralized before it reaches the passenger. There is a second engineering implication that has received almost no attention in automotive media. The traditional argument against placing heavy components near the wheels, in what engineers call the unsprung mass, is that additional weight in that zone makes the wheels slower to respond to road inputs. Heavier unsprung components degrade handling. This principle has historically been cited as a fatal objection to in-wheel and near-wheel motor architectures. The DiSUS system invalidates this argument structurally. Because the motor is active, it does not carry its mass passively. It can drive the wheel downward at accelerations exceeding gravitational force, beyond 9.81 meters per second squared, actively pressing the tire into the road surface to generate grip in conditions where passive systems would lose contact entirely. The suspension is no longer an impact absorber, it is a downforce and traction management system. DiSUS exists in three distinct configurations, each optimized for a different performance priority. The DiSUS Z, fitted to the Yangwang U7 sedan, targets absolute comfort. The engineering goal is seamless isolation from road topology, the complete erasure of surface texture from the passenger experience. Driving impressions from journalists who have spent time in the U7 consistently describe a disconnection from road disturbances that makes the ride quality of a Rolls-Royce Ghost feel comparatively approximate. The DiSUS X installed in the Yangwang U9 supercar represents the performance extreme. Peak suspension power output, 36 kilowatts. That figure, dedicated entirely to controlling wheel position, exceeds the total drivetrain output of many small city cars. The footage of the U9 lifting all four wheels off the ground simultaneously is not a marketing spectacle. It is a controlled demonstration of instantaneous force deployment across all four corners. A vehicle weighing over 2.5 tons leaving the ground requires a specific explosive coordinated mechanical event. DiSUS X produces it on command. The safety implication is equally significant. The U9 can sustain controlled operation on three wheels. In the event of a tire failure at speed, a scenario that has caused fatalities in conventional high-performance cars, the DiSUS system detects the pressure loss within milliseconds, retracts the damaged corner clear of the road surface, redistributes structural load across the opposite diagonal corner, and applies torque vectoring across the three remaining drive motors to maintain directional stability. Potentially catastrophic mechanical failure becomes a recoverable situation. The DiSUS in the Yangwang U8 applies electromagnetic and hydraulic integration to serious off-road use. 155 millimeters of independent suspension travel per corner. Intelligent cross, axle load management, and a sealed emergency float mode enabling water propulsion using spinning wheels. Against this, Porsche's most advanced suspension offering in 2026 is a 48-volt active anti-roll bar system. It is genuinely sophisticated engineering within its design constraints. It cannot, however, lift the vehicle off the ground. It cannot recover gracefully from wheel loss at speed. It cannot scan the road surface ahead and preemptively reposition the suspension before the impact arrives. It is the most refined version of the same fundamental compromise that has existed for 140 years. One final technical dimension deserves serious attention: regenerative energy recovery. Conventional hydraulic damper absorbs kinetic energy from vertical wheel movement and dissipates that energy as waste heat, permanently lost. The DiSUS linear motors, because they are magnets moving through coils, automatically generate electrical current when absorbing road impacts, feeding that energy back into the 800-volt battery pack. The rougher and more irregular the road surface, the greater the energy recovered. Infrastructure degradation becomes a net positive for the vehicle's efficiency. This is precisely the energy recovery mechanism that made the Bose electromagnetic suspension commercially impossible in 1990. The 800-volt EV platform solved it. And the traditional automotive centers in Detroit and Stuttgart did not see it coming. For generations, the most respected brands in performance automotive engineering, Lotus, Porsche, BMW M Division, built identities around something that could not be formally documented. The intuition of master chassis engineers, men who spent entire careers with their hands on springs and dampers, chasing the precise mechanical balance that gave a specific car its specific character. That knowledge was embodied, not transferable. It was the soul of the machine. That era has ended. With DiSUS, the character of a vehicle is no longer shaped in metal or discovered through decades of iterative physical testing. It is written in software: ride stiffness, rebound damping curves, roll gradient response, all of it encoded as numerical variables, deployable over the air, tunable in real time based on aggregated fleet data from thousands of vehicles in active use. A firmware update can transform the same physical hardware into a configuration that mimics a GT3 racing car, or recreates the pillowy float of a 1970s American land yacht. The mechanical platform is fixed. The personality is a parameter set. This is not where the story ends. It is where it begins. Because the consequences extend well beyond ride quality metrics or suspension reaction times, they reach into intellectual property, competitive positioning, talent pipelines, and the long-term commercial viability of brands, whose entire premium justification rests on mechanical mastery. The road hasn't improved. Infrastructure hasn't advanced. The machine simply learned to make the road irrelevant. That is not an incremental improvement. That is a category redefinition. And it happened in Shenzhen, not Stuttgart, not Munich, not Maranello. The industry has had 140 years to solve this problem. It built a comfortable consensus around why it couldn't be done. China didn't join that consensus. It ignored it entirely.